Hey everybody and welcome. In this video I'd like to talk about the derivative. And the derivative is just a mathematical concept that helps us understand a function's behavior. And it allows us to magnify on a given point along an equation's output or range. And we can see how the output changes as inputs change. And this is valuable. And this process of finding the derivative is called differentiation, which is where this title of differential calculus comes from. Now, understanding the instantaneous rate of change of a function can have a lot of applications, a lot of real-world applications, and making it useful. And the first very original intended purpose of the derivative was used by Isaac Newton to model the relationship between distance, time, velocity, acceleration, momentum, what we call Newtonian physics or classical mechanics. And to go on this further, to go into further depth on this, he showed us that the relationship between distance and time, where velocity is the derivative of distance, and then he gave us the second derivative, which is the relationship between velocity and time, where acceleration is the derivative of velocity. And we can really take this idea of the derivative and differentiation and apply it to many different sectors and different industries even today. For example, we could look at the relationship between new money printed and time, where inflation is the derivative of a price index. We could observe the relationship between genes, different genes, and time, where genetic variation is the derivative of a gene pool. We could even look at the relationship between ASIC computations and time, where the hash rate is the derivative of Bitcoin mining. So you can see there are plenty of different applications we could look at and use to study whatever phenomenon you are looking at observing. And this ultimately leads to multiple variables that you have to be concerned about, and there's actually a process for understanding that, which is called implicit differentiation. And this is useful because most of the real world doesn't just have a single variable to be concerned about. There are many influences and factors impacting an equation. But it was actually this gentleman here, Pierre de Fermat, and this gentleman, Isaac Barrow, I think it's pronounced Barrow, who were mathematicians that really gave the first conception and idea of the derivative in practice and gave us the first evidence of its existence. And then came along Isaac Newton and Leibniz, who really unified differentiation and integration to give us what we have in modern calculus today. Really specifically, Newton used differential calculus to understand and model the relationship between objects, which I talked about briefly already, and then Leibniz gave us the notation we still use today, as well as a systematic approach to teaching it and understanding it that is used in schools and it is widely used across industry and sector. So with that background, I'd like to jump into a problem, a very complex problem that uses as many differentiation operations as possible to give us the best intuitive understanding of differential calculus as possible. So let's do that. Now, when we think about the derivative, it's important that you have a grasp of limits and continuity already. And so I recommend watching my video on limits and continuity, which I'll leave in the description of this video. Now, the first thing I want to unravel and go over is the idea of, or not an idea, but the notation for the derivative. And there are several different notations, but I'm going to focus on two of them. And the first one is the Leibniz notation, which looks something like this. Maybe you've seen it before, where it's the derivative with respect to x. Now you can also have a notation with any symbol in the denominator, so the derivative with respect to y, or with respect to z or f, whatever is relevant to what you're studying. And we use this symbol when we are saying that we are taking the derivative of that term. So assuming we have this term here, x squared, we would put this derivative operator in front of it to indicate that we are taking the derivative of this term with respect to x. And that would just be 2x. And you'll see in a moment here why that is. The other notation is the Lagrange notation. And this is going to be represented. You have some function with an input x, and you'll put this apostrophe here to indicate you are taking the derivative of this function. And we can even denote it as with 2 apostrophes, and we have the second derivative of this function f of x. So these are the 2 different notations for the derivative. Now, when we say the derivative, we're talking about the rate of change in a function. And there is actually an algebraic definition for this. And I'm going to stay away from using graphical concepts or graphical visuals until the end, because I think it's valuable to go through all of the algebra first, because that is more challenging and it forces you to think and focus more than if you just look at a graph and be like, oh, okay, now I get it. So with the definition, it will look like this. We will take the limit as x approaches some value a for f of x minus f of a over x minus a. And this can be a bit intimidating, but if we break it down, we can see that this is really just telling us to take the limit as that output changes and the input changes. And to make this simple to understand, or clearer to understand, we can think about the formula for a slope, which you've seen before. It's the difference between 2 y points and 2 x points. So the change in y over the change in x. And so that's all we are doing here as well. It just looks different. But really f of x and f of a are the output values. This is y2 and y1, but written as the function output with an input of x and the function output with an input of a over the change in x, our input values. So really, all this is a way of talking about a slope of the tangent line. And fortunately for us, we live in a time where we don't need to apply this definition in this algebraic form every time we are looking at an equation or trying to solve a problem. And instead, we have devised rules that have been proved through using logical proofs by other mathematicians, building off the work of even more previous mathematicians. And they gave us several rules we can use to make it easier to solve problems. And those are the power rule, the product rule. And now I'm not going to write out all of these rules, but it's very easy to look these up and they're fairly easy to interpret and understand. So you should definitely do that before we do the problem that I'm about to run through. Quotient rule, and we have the chain rule. The chain rule might be slightly more complicated to understand, but I am going to focus and I will use the product rule, the power rule, and the chain rule when working through our problem. So these are easy to look up and you should do that. And then I will give us, I will use some trig trig functions in our problem. So just briefly, I will summarize the derivative of cosine of x and sine of x. And so the derivative with respect to x of these two functions is, so the derivative of cosine of x is negative sine of x. And it's pretty cool why this is, and you can also find the derivative of sine of x, which is going to be cosine of x. Okay, so our equation for our problem is going to be f of x is equal to the cosine of x to the fourth power. And this is the same thing as cosine of x raised to the fourth power. These mean the same thing. And so we want to find the derivative of this function. So I will notate it as such. The derivative of f of x is going to be equal to, and in order to figure this out, we will apply the chain rule. The chain rule is right here because we have cosine of x within raised to a power. So you could think of the inner function as cosine of x and the outer function as x of 4, x to the fourth power. And so if we just apply our chain rule properties, we get 4 cosine of x to the third power times the derivative of the inner function, so cosine of x, which is negative sine of x. If we move our minus sign to the front of the line, the derivative of f of x equals negative 4 cosine of x to the third power sine of x. And that is the derivative of our original equation. But we're not going to stop there because we want to find the second derivative of this function. And in order to do that, we will have to we have a product here, so we have to take the product rule, and then we still have our inner and outer function, so we will have to do a chain rule as well at some point. So if we go ahead and apply these rules for the second derivative, we will do the product rule first. I think that would be the best option. So let's move our constant out to here, negative 4, and then we will do our product rule, and we get the derivative of this first term, which is 3 cosine of x to the second power times the derivative of the inner function, cosine of x, so again, negative sine of x, and then we multiply that by the second term of the product, so it's just sine of x. And then we add them, and we take the original initial term in our product, which was cosine of x to the third power, and we multiply that by the derivative of sine of x, which is cosine of x. And so now we have our equation. We can move this negative sign to the front, and we get negative 4 times negative 3, and we have, let's just rewrite this so I can see, cosine squared of x times sine of x times sine of x again, which we can just write as sine x squared, plus cosine of x, looks like to the third power plus another one, so to the fourth power. And this here is our second derivative. So we applied the product rule and the chain rule, and we even did the chain rule twice in order to get the second derivative of this seemingly simple function of cosine x to the fourth power. And we get this as our answer. So now that we have the derivative, the second derivative, if we input x's into these, which I'm not going to do, but you could, and we would get some sort of output that would have a graphical structure as I'm about to show you. And so we can see here each individual graphical structure for our original equation, our first derivative, and second derivative. And when we look at these equations, now we can kind of think about what we mean by the line tangent to the graph. And so when we have cosine x to the fourth power, we find the derivative and we get this, -4 cosine of x to the third power times sine of x. Now if we input any value into the x for this function, we get the slope of the line tangent to the graph. Or another way, we're finding the limit of the secant line for any value we plug in to x. And so if we plug in pi, we would probably get, it looks like a slope of 0 right here. But we could do it anywhere. We could do it along here. And this even extends to the second derivative. We could plug in any value for our x into the second derivative equation, and we get the line tangent, the slope of the line tangent to this graph. And so we could do that for anywhere we are interested in when we're studying something. And so that's what the graphical nature of the derivative shows us. But we also know that we can have an equation that doesn't have a derivative. And for example, I have this function here, f of x equals the absolute value of x minus 2, and that would look something like this, where there'd be like a v at the point 2 on the x-axis. And if we tried to find the line tangent at this point on the graph, it would have an infinite number of different lines we could take where we would get the slope. And so there is no derivative here at this given value of 2.